For a long time, we thought space and time were a fixed stage, a rigid background where the drama of the universe played out, but the stage itself never changed. This idea started with Aristotle. He believed that the natural state of any object was to be at rest and that heavy objects fell faster than light ones because the earth pulled harder on them. But the Aristotelian tradition claimed you could figure out the universe just by thinking about it. No checking required. That changed with Galileo. While the story of him dropping weights from the Leaning Tower of Pisa is probably a myth, he did something equally brilliant. He rolled balls of different weights down smooth slopes. Galileo found something shocking. If you ignore air resistance, a heavy lead weight and a light feather would increase their speed at the exact same rate. Isaac Newton took this data and built his laws of motion. He proved that force doesn't just create motion, it creates acceleration, a change in speed. But Newton's laws killed an old idea: absolute rest. Imagine you are on a train moving at a constant speed. If you play ping pong, the ball obeys Newton's laws exactly the same way it does on a stationary table. If you close the curtains, you cannot tell if the train is moving or if the earth is moving underneath you. This meant there was no absolute position in space. Events look different depending on where you are standing. But both Newton and Aristotle still agreed on one thing: absolute time. They believed time marched on instantly and identically for everyone, everywhere. They were wrong. The cracks in absolute time started with the speed of light. In 1676, a Danish astronomer named Roemer noticed that the moons of Jupiter seemed to be late in their orbits when the Earth was far away from Jupiter. He realized this was because light took time to travel that extra distance. Light had a finite speed. Fast forward to 1865. James Clerk Maxwell unified electricity and magnetism. His equations predicted that light waves travel at a fixed, constant speed. But here was the problem. Newton said there is no absolute rest. So if light has a fixed speed, fixed relative to what? Scientists invented a substance called the ether to explain this. They thought light waves traveled through the ether like sound travels through air. In 1887, Michelson and Morley tried to detect this ether wind by measuring the speed of light as Earth moved through space. They expected light to be faster in one direction than the other. Instead, they found nothing. The speed was exactly the same, no matter which way they measured. Enter Albert Einstein. In 1905, this unknown clerk suggested we just drop the ether. He proposed that the laws of science are the same for all freely moving observers, and, crucially, that the speed of light is the same for everyone, no matter how fast they are moving. This is the theory of special relativity. It forces us to abandon absolute time. Why? Because if we all agree on the speed of light, but we disagree on the distance the light traveled because we are moving relative to each other, we must disagree on the time it took 18. Time is personal. Each observer has their own measure of time. To map this, we use space-time. Imagine a stone hitting a pond. Ripples spread out in a circle. If you stack those ripples up over time, they form a cone. The future light cone contains everything you can affect. The past light cone contains everything that could have affected you. The region outside, that is the elsewhere. Nothing there can affect you right now because information can't travel faster than light. If the sun went out right now, we wouldn't know for 8 minutes. We are in the elsewhere of that event until the light reaches us. Special relativity was great, but it had a flaw. It didn't work with gravity. Newton's gravity acted instantly across distance, which implies infinite speed, impossible in Einstein's universe. In 1915, Einstein fixed this with general relativity. He suggested gravity isn't a force like magnetism. Gravity is the result of space-time being curved by mass. This theory made a wild prediction. Light itself should be bent by gravity. During a solar eclipse in 1919, British scientists looked at stars near the sun. The sun's gravity bent the starlight, shifting the star's apparent positions. Einstein was right. Space and time are flexible. This curvature affects time too. General relativity predicts that time runs slower near massive bodies. This was proven in 1962 using clocks at the top and bottom of a water tower. The clock at the bottom, closer to Earth, ran slower. This is why your GPS works. If satellites didn't correct for this relativistic time difference, your position would be off by miles. This leads to the famous twins paradox. If one twin stays on Earth and the other travels near the speed of light, the traveler returns younger than the one who stayed. It's only a paradox if you still believe in absolute time. But in relativity, there is no unique now. Before Einstein, we thought space and time were a static arena. Now we know they are dynamic quantities. Space and time affect everything that happens, and everything that happens affects space and time. This realization set the stage for the next great discovery. The universe isn't static. It is expanding, with a beginning and perhaps an end. But that is a story for the next chapter. Thanks for watching.